Hello to you all. My name is Pawel Cyrta. Uh, Not at all, it's a very common mistake. I'm really happy that you are all here. It's numerous people. I should just schedule bigger room. My topic is about sound, yes, and sound is something that is not so common in the space of deep learning in terms of like common view. Mostly it's about NLP. Mostly it's about images. All those domains are very interesting, but I would like to introduce you to a brief look on how to model sound in a particular way, only as a sound. Oh, we'll see later. So my general agenda is a very simple one, and I would like you to just pick some general ideas and about sound representation, and also how to use Python, how to use some number of libraries to represent, to encode those sounds, and then use that into other machine learning algorithms for particular purposes like classification, extraction, etc. However, my general heart is in music creation and soundscape, sound art world. So I will show you how to make sound by computers nowadays. And I hope you will take some time and maybe show it to your kids whenever they will grow up. Okay, so who I am. My name is Pawel Cyrta. I'm a research engineer in various companies. I have like 15 years in different domains. I was working on the S-Voice, now Bixby speech synthesizers in Samsung. I was doing speech and speaker recognition in a couple of companies, and also I was lecturing sound engineers and composers in here in Warsaw University of Music University. As my artistic background is, I was introduced to that around 2009, and I was bringing up a lot of people around new technologies and how you can shape those, creating various music controllers also in Python. Here, when we are here in Copernic in 2015, there was a sound installation during summer, like during 6 weekends, based on some parts was in Python, most was in Super Collider. It's a very bizarre asynchronous language only specific to sound generation. And it was a mixture of all possible things like taking data and sonify that. So analyzing, clustering those data that were coming out from trains, from buses of Warsaw, and also sampling and recording all different parts of Warsaw. And then using, for example, granular synthesis. I will not. Well, you can check it out what it is in Wikipedia. Just to change the sound and also to orchestrate the whole piece. On those boxes, there were different sensors, like haptics ones, like ultrasonic. There were also cameras. There were also different microphones and different pickups. So whatever there was in the box, for example, like screws, were recorded, but also those things triggered the sound in the whole piece. But that's about me. Let's start about sound. So when we want to have a sound, we need to have some kind of tool instrument, and mostly it's about guitar and different kind of plugs. That's the analog electronic world, what is called an analog, but analog I would say that is just acoustic guitar, not any without wires. So, but people are really into like taking any object, hitting it or doing whatever, and then record it. And later on, you can sequence that, you can group that, you can mix that into a piece that later on will be ported out as a cassette or CD or other file medium into some kind of distribution and the listener. It's a whole different idea to talk about how different is the process, how it changed throughout the years. Right now, the process is so simple. You can mix, record, edit, a little bit master, you have file, and then directly you send the file to Spotify, Deezer, you name it, and they just they use their own mastering device algorithms to enhance the sound and put them into their collection. So you really cannot have a control over your piece, how it will be listened to. That's why I like live performance. And of course, you can use DAW, or you can use, yeah, you cannot hear it. Wait a second. Yes. Okay, so I will. M? So this is a Excel file that is changed into sequencer. Sequencer is a very simple way of representing of music. You have beats, and you can have on the rows, you have instruments, and then on the time you select where it will be played. And you can do it whatever. And this way of this kind of software was done by old people, like do it yourself in 80s, by their own, on Atari, and they program it by their own. Right now, you generally have those kind of big digital audio workstation when you don't know what is inside of it. And of course, you can even use some. I'll just put a portion of it. I don't know whether it will render. You can, of course, use Ableton or some kind of interactive tools with what is called graphical programming, visual programming languages, with a lot of randomness, with a lot of ideas on generative algorithm, and just simply generate the piece, soundscape. Yes, so I don't know whether this will be. So this is a pure data, it's an open source environment, a graphical environment, that can be controlled from Python as well. Those blocks are just some kind of functional blocks. Nevertheless, you see that those scripts, this is a program for people that don't really know how to program graphically, like creative people are taught during studies for this kind of machine. This kind of language, just to enhance their possibility. There are different tools. They can create their own tools. They can create their own environment when they just have their own, like you would just set up the whole workstation when you all have the scripts and all ready to render. They also can create those kind of scripting environment. And in fact, most of the good and known studios or composers, they started or they're right now using such tools like Hans Zimmermann. He had on the start he had Max MXP. Right now he has 6 programmers only for him, just to make all those kind of little things as orchestration, as a tools for creation. And just to where this is bringing us. That right now with the deep neural networks, also of course GANs and algorithms that are give us possibility to render whatever we like, from text to image to sound. This is a pure synthetic artist, Yono, that is just like 2 weeks ago, just started to have their own premiere on Spotify. But this is not a new thing. This is just a hype on the USA, because in Japan that was 20 years ago with Vocaloid, which is kind of sorry, not Vocaloid. Vocaloid was the technology. Oh, I forgot the artist. Shame on. Nevertheless, this artist and a couple of others are virtual artists, and they have even live performance when they are streamed into the screen, and the voice, the music is either synthetically created upfront or just created live. And this technology was 2010 when it was really good. It started in around 2000. Yes, so my message to you is that if you are already, if you're not creating right now, just started. If you don't really use a guitar, keyboard, or whatever you already been using, try to think to enhance your workspace and use whatever tool is there, Python or Pure Data or just in order not to expand your point of view and innovate on the art form, because the DAW really shape the music into this 3 minutes 30 seconds, and right now even 2 minutes 15 seconds pieces. That's the music pieces on Spotify right now starts with a chorus, because people just listen to chorus, okay, it's good. And then the whole part begins, like after 10 seconds. The general purpose of the computer for music and sound production is to be a creative enhancement and to assist. Assist, I mean, when you generate a music piece, it's not to just to produce absolute solution, but assist you. So you are a curator for your data. As a curator to your data, you are a curator for the result that is generated. You generate multiple times of various conditions, whatever, and you pick the best one. This is one of the flows that workflows that you can follow. But yeah, let's deep dive. So basic concept. If you don't know what is sound, I could speak like at least 3 hours. This is generally a physics, so you see the little particles of the air moving up. If you digitalize, you can have different dots, so values per microseconds. And then you can traverse it into frequency domain, into frequency representation that is on the left up corner, and if you want to really plot that as an image, so through time, you can have spectrogram. And this is basic thing that people are using in deep learning. So using sound, visual representation of a sound through time. And you can, if you want to have a very simple classifier, you can put this image into ResNet or VGGNet or whatever, and have a simple already trained or pre-trained VGG on ImageNet or whatever, and have a very good, decent classifier of I don't know. I once did this classifier for lip smacks for sound. To analyze, to clean up the data sets of speech recordings. And then you can just throw out this. Normally, I just, sound engineer would spend like a week cutting out on DNW all those lip smacks. And if you can just have this simple analyzers and knowing where those are places, you can either then manually review that or just have a simple Python script that's just remove that block and saves the file for later. All right, so, but if you want to have a sound, you need to have basic equation of a sound, which is sinusoid, that can be created in and playback in Python. But those parameters are most of the instrument sound is timbre, pitch, and dynamics. And this is what the MIDI sends to the MIDI controller or keyboard or whatever MIDI instrument there is, sends to some kind of sound synthesis devices. You can also create with there is a possibility to create using, if you know what are the way of equations of from physics, if you just skip the physics books on sound creation, you can find some equation, put it into the function called dump wave, for example, and some it's already in the library called Wavebender. You can just synthesize harmonics of particular sound, of a sound of a violin, and have that already available to you. Sound is not so good as standard one, so however, the general case is that if you analyze music or sounds, you need to see it as a sequence model, as an event-based or sequence-based domain machine learning problem. Mostly it can be described and is described in a kind of physics mathematical equation. But let's put it that commonly the music production software companies and also the studios are so into the very good quality of sound. That's why they just use a software that's played back simple samples of sound into so like 636 recording of a particular note on an instrument, put it in the software, package it, and expand that. You can, of course, use right now is very common in some pop music and also rap music for samples like bass parts to use FM synthesis. I will not cover that, but the FM synthesis is also kind of signal processing algorithms. And what I wanted to talk about is about parametric models, which is a model that will that have a general some idea of a sound, of a model, and have parameters to it. And in order to grasp the interior of the model, someone put the knowledge up front or use features as a rule guide to traverse the sound model. One of this is very simple sound source filter model. So you assume that there is a sinusoid or a noise from, for example, from your glottal or from the string. String is very sinusoidal, but there is a little noise in it from when it's damping. When it's damping, also it changes some frequency characteristics. So that's why you put general filters on the frequency domain and change the timbre of the sound. And that's in this simple way you can create a certain timbre. Also, you can have this taken this the sound wave form into frequency domain and analyzing it. Where are the components? Where are the most high energy parts, which are probably sinusoids, because people were analyzing that for like 20 years. Most of the speech codecs that were in GSM 1, 2, and 3 use and right now also some parts of your Bluetooth very bad connection also use this kind of model, that it's searching for most high frequency parts, assume that it's sinusoid, and the rest, and analyze what is the rest, and create a model, stochastical model of the noise, and then glue it together. This is the diagram of this. Since I have time is passing, you see that most of the things is about signal processing and recreation of a sound as a parts of the harmonics of the sinusoid and the noise. There is a tool, very good tool, made from people from Yamaha that's used. The software is also used by in the Yamaha synthesizers. It's called SMS tools, and SMS called sinusoid modeling software, which you can just recreate, redo, and like do analysis of a sound. You can change some of the representation in frequency. So, for example, you can change the value of certain formants and then resynthesize, or put a filter on it and resynthesize. And this way, you can shape the sound of a violin in a certain way. You can, for example, you never heard a violin with a third formant moved into up high or something. You can shift the timbre, because I didn't tell that. The timbre of a sound is, the characteristics of the timbre of a sound is the way how the harmonics are, what are the frequency of certain harmonics and what are the amplitude of that. So when you change that, you generally change the whole timbre, whole sound of the particular note. But yeah, people like in 2010 or 2005-10 already have that model, and they wanted to make the sound better. So they started to use more and more machine learning, more statistical model, in order to optimize to fine-tune the parameters. Most of those parameters for like you would like to create a violin synthesizer, let's say, right? You can of course sample that, but you can also make a generator like this, in synthesizer like this, using this technique. Why? Because it will be so small, the model will be so small that you can put it into very little chip and sell it in the millions, like Yamaha or Casio or whatever. And if you tune the parameters in various conditions, then you can shape the sound as well. You can put a number of knobs as a controlling parameters into the model. Yeah, and one of the that is for speech. If you don't use SMS library, you can use World speech model, which is a continuation of straight. Very good speech synthesizer model, the representation of the speech, and the model generally analyzes where are the pitch components, the form, where's the pitch, what is the pitch, what are the formants, what are the harmonics, and then extracts with this information the stochastic model of a noise floor. Yeah, but what about neural models? One of the neural models that is so often brought up is the WaveNet. And people from Magenta project from Google, they invited a number of artists, of new media artists, some kind of researchers, to collaborate them on using the WaveNet as a tool for modeling the sound, so in different ways. So, for example, you can there is a Jupyter notebook here. You can play with it. I will later. This presentation will be available. You can generally the model was trained on all possible instruments, like thousands of instruments, and you can. Generally, using parameters of latent variables that you this model is was trained on conditional on some variables, and changing that, you can change what is the sound between violin and piano, what is the sound between voice and saxophone. You can do with this with model. The general presentation here is dilated convolutions that are later on processed into some kind of distribution around values of the samples. There is Magenta project, as I said, and it's very well documented. There are lots of examples, and here's one of the to encode the sound. You can then synthesize that, and also if you want, you can change the. There are in the Jupyter notebook there is a examples how to shift some parameters in order to find the right sound. Recently, there is also by the same group, there is a GAN synth. GAN, probably you already heard about that. The difference is this, that there is a you can generally the samples from the generators are taken from specific like spherical Gaussians, not normal Gaussians representation, and also that it goes through various convolution layers with some ResNet connections both on the same on the generator and the discriminator. And they found out that if you analyze for a very short period of time, like instantaneous frequency, which is 1 millisecond, generally the frequency components, like it's doing the same like sinusoidal modeling. It's find out that there are some kind of strips around that, and but however, it also gives you all those lattice variables to tune the model. For particular sound, and as previously, you can take the code and play with it. It's briefly quite simple one, but you probably also want to do something with recording sound, and recording sound is tricky because it's recorded, and you cannot really change it. You can filter out. You can delete some portion, but you cannot really unmix the sound. So if there are like 3 components of the sound, like 3 guitar, bass, and piano, you cannot really split it up. It's already done. But there are 2 recently this year and last year. There are 2 projects that you can use to just take your drum patterns from your best artist. Of course, it's copyrighted, probably in some part, but you can sample it. You can use it in some kind of hip hop, or at least put it into analyzer to analyze the beats and have the same MIDI representation of the beats, and then on a DAW and synthesize that again. Generally, this is UNet architecture with various convolutions and BLSTMs. There is also a splitter from Deezer, a little bit worse, but it depends on what the bass is a little bit better, but the voice is worse than Unmix. Yeah, this is a kind of holy grail for many people from like 20, 30 years to if you like to listen to orchestra, or like you want to really reflect on some on particular portion on this particular instrument, like you really like this bass player, and the mix is so dense that you cannot really listen to it. But here you are, it's there in Python. And you can also synthesize the voice, if you like. There is a Mellotron from NVIDIA group, generally based on the tachotron representations, which is encoding of characters through convolutions, through some LSTMs, back to some tricks on the upper here into MEL spectrogram, and the MEL spectrogram is put it into a WaveNet vocoder and creates a sound. If you condition that on a particular style of playing or a particular instrument, there you have it. I will leave you up with some couple of papers, and also, is there any questions then?
Thank you very much.
From me.